different topics, and recently she received a grant, a 3-year MRC grant, an early career award, for studying causal inference in health economics and how can this be embedded within economic evaluations. So, as part of this grant, I suppose, this is part of her work. It's not published yet, but so it's part of her new work. So, Noemi, thank you for coming, and good.
Thank you very much for the kind words, and thanks a lot for inviting me. Do I speak loud enough? Great.
I'm sorry.
What?
I forgot our routine. So our routine is that we first introduce ourselves, and I'm going to start. And I'm Petros Ivanou. I'm a health economist at THETA, and I forget sometimes.
My name is Joanna Biczetti. I'm a research librarian. And also wanted to mention that we also have this online, so we might have some questions from the online participants if we have any.
Okay, so I'm Bea Alexander. I'm a scientist with Public Health Ontario and assistant professor at the University of Toronto. And I'm Anna. I'm a health
Nicholas will take some presentation.
I'm Manuel Young. I'm an epidemiologist at Public Health Ontario. I'm Noemi Kreif.
Brian.
Thank you. So thank you. This is work in progress, and I would really like to have a conversation. So please feel free to ask questions on the way, especially around clarification of notation. So, this is our acknowledgement to my collaborators. This work was based on some of my postdoctoral training visit at UC Berkeley, working with great biostatisticians, Maya Peterson, Mark van der Laan, who greatly shaped the way I think about causal inference. I hope that I will be able to transfer some of that excitement to you today. And my colleagues, Richard Give and Bianca SHTM, and Robert Tasker, the clinical collaborator, and funding from the MRC is greatly acknowledged. Okay, so the hardest part of my presentation is coming now. This is my team at LSHTM, which has been recently branded as THETA, and yeah, I was following the decision process from Berkeley, so I didn't really participate. Except I'm pretty sure I voted for THETA because the alternative was HEPTA, which sounds really horrible. So well, I guess we need to work on like differentiate in terms of branding, and you guys should take it as a compliment that we think our name is great. So yeah, what we do, now we got through that, we basically a bunch of health economics, yeah. Not yet? All right. So what do I have to do to get the apology in the name of my whole group? It's okay? Apology received. Great. Okay. So I mean, the group is small and informal. It's at the Department of Public Health at the London School of Hygiene, and we do causal inference, economic evaluation, utility stuff, and policy evaluation. And you can express your questions and opinions at the following email address. All right. Okay, so the motivation for my talk is on a more positive side, is around an increasing interest in evaluating health interventions which are administered over multiple time periods. And I would like to give you a couple of examples to motivate this talk. So the first example is around chronic conditions. When we think of evaluating, for example, a drug treatment for type 2 diabetes, we rarely think in terms of treat with the drug and just check the outcomes 20 years later. Things happen. Drug treatment gets intensified, and that's mostly due to the health is changing. Something has to be done. So it makes sense to define treatments as longitudinal treatment regimes, as opposed to treatment at one time point. Second example is motivated by very acute methodological interest in oncology trials. Patients switch treatments. They start on something, and very often they don't finish the course on the treatment they started on because there was progression, there was toxicity, there was no response. What to do in these cases? Should we think of treatment switch as something bad? We have to adjust for it statistically, or maybe, as the third example shows, we could think of it as something which is more realistic. Something which is actually should go into a future clinical guideline, the sequencing of treatment, potentially responding to the individual course of the patient. So the evaluation of these individual treatment rules and sequences is also motivation for looking at these methods. What are the data sources which can be used for evaluating these longitudinal treatment regimes? Well, starting from the most ideal ones, ideally, randomized trials would compare whole treatment sequences. This is very rarely done. It starts being taken up, but it's very rarely done. This ideal study design could be, for example, sequential randomized trial, where from time to time patients are re-randomized for new treatment arms. What we do have, though, very often is have trials where patients start something and then switch, or they don't comply. So trials with protocol violations give us the potential source of doing such evaluation. And more messy, but actually much more common and very, very relevant, we do have the observational data. We have increasing large databases, routinely collected data, which actually gives us a great opportunity to compare treatment sequences, to compare longitudinal treatment regimes. What is the main challenge here is what to do with the main problem of the observational data, confounding. Because confounding here will be actually a more complex issue. It will become time dependent. And I give you a very simplistic example of what we actually mean by time dependent confounding. Sticking with the example of diabetes, the question is, considering 2 time periods, maybe 2 years, what is the effect of giving certain antiglycemic drug treatment over 2 years? A0 is the treatment in the first year, A1 is the treatment in the second year. I'm sneakily introducing notation, by the way. So A will refer to treatment throughout the whole talk. And 0 is the first time period, and 1 is the second time period. So the question is, what is the effect of such treatment? The risk of cardiovascular events, outcomes will be denoted by Y. So we have A0 and AY, and we have some outcomes. So what we want to know informally is how treatment in the first year and the second year affects risk at the end of the second year. Well, these treatments were not necessarily randomized. So let's say now the first maybe was, but the second year treatment is not randomized. Something changes over time. It changes due to some patient characteristic which happens. For example, what's this level? HbA1c level, so which is the biomarker for how well the blood sugar is controlled, increases. So this is L1. L1 is a confounder because it affects the risk of the event, but it also affects the treatment of interest. So the red arrows show that there is confounding going on here. And also this confounder might be actually very likely affected by the treatment in the first year, which makes it time-dependent confounding, and which makes it impossible to adjust for this using traditional regression methods when you just chuck in everything on the right-hand side and hope that things get taken care of. Yeah?
When you're referring to treatment of interest, are you referring to the combination of A0 and A1, or you're referring to A0?
The combination of A0 and A1, yes. Yeah. But this is a really good question. Here I'm deliberately keeping this a bit vague to spend quite a lot of time in defining what we mean by the treatment, but both. So by treatment, we mean something which we would like to be ideally able to intervene on. And we would like to be able to intervene on both the drug treatment in first and in the second year. Yeah. So traditional regression methods fail. We need specialized methods which can deal with time-dependent confounding. Well, luckily we have some, actually, where we have quite a bunch of appropriate methods for dealing with time-dependent confounding. Most of them developed by Jamie Robbins and his colleagues at Harvard over the last 10 years, but other biostatisticians and statistical innovators have also joined in this work of providing methods to deal with time-dependent confounding. I'm not going to talk too much about these methods today, except for the last one, because that's what I'm going to demonstrate. But what I'm going to spend much more time with is what are the general issues which the application of all these fancy estimators needs to consider. And these are the following. The first one, what are actually the different regimes that can be compared? So this goes back to your question. What do we want to intervene on? How we imagine that? What is the actual causal parameter we are after? Is it a risk? What is it? We have a look at that. Can these causal parameters be identified from the data? And then, how actually we specify the models which will underlie our estimators of interest? All these questions have to be answered to use any of those fancy G methods above, and I'm deliberately only picking one to demonstrate these issues. So this is the objective of the talk. I would like to demonstrate the great opportunities, but also the challenges of causal inference for these longitudinal treatment regimes. In doing so, I will try to actually answer real clinical questions, yet unanswered clinical questions, which is when and how to feed children at the intensive care unit. And if I have time, I also briefly outline a very innovative and very attractive estimator for this issue, the targeted maximum likelihood estimator. This is work in progress. Any input and comment is welcome. Okay. So I jump into the motivating clinical question straight away. How this project happened? We have a clinical collaborator working on evaluating a clinical trial, a randomized clinical trial for glycemic control for critically ill children. So we had this guy around who wanted to do something more with the data, and then he wanted to meet us, and he said that, well, there is this feeding thing recorded here, and I really would like to know how these children are actually fed. Is this actually according to the guidelines? Because I have this suspicion that the way caloric intake, daily caloric intake is calculated for children is kind of wrong, because it's based on the body surface and the weight and the height, and these proportions are just different from children than for adults. So he had this hypothesis that children at the intensive care unit might be actually fed too much because of the way the equations are set up. And there's really very little known about this. There's very little known already about how much adults at the critical intensive care unit should be fed. There are competing hypotheses. First one, well, you know, you shouldn't starve people. In order to get better, you should give some feeding. But also, if patients are maybe recovering from something very severe, then actually absorbing those extra calories can slow down recovery. So there are competing hypotheses, and we don't know much about how this works for children. Definitely no randomized controlled trial evidence. So that's why we were very excited to see that in this randomized trial we had in the control of hypoglycemia for RCT, we had this feeding recorded for every day. And originally, what we wanted to look at is the dose-response relationship between how much calories to give and what the outcomes are. The primary outcome of this trial was days without mechanical ventilation, which is standard critical care outcome. I started looking at the data, like actually not even the data, just the way the data is formatted, the CRF, right? I think it's called CRF. And it very quickly came clear that this is actually longitudinal treatment. These calories change every day, and very likely as a response to something which happens to these children. They get better, they get worse, they get on mechanical ventilation, they get off mechanical ventilation. So simply taking an average over the first 10 days and having a look at the effect of those calories on the outcomes are would be wrong. So this is what motivated this whole methodological inquiry of what the best method to actually adjust for this time-dependent confounding. So how does the data look like? What we could actually use to answer this clinical question of the relationship between caloric intake and outcomes. So we had 30 days follow-up. We decided to focus on the first week for reasons of data becoming very thin and also to test out the methods. So here we focus on the first 10 days. We measure a bunch of baseline confounders, baseline characteristics, which I denote here with L0. These are the variables which were collected in the randomized trial, and they were actually the variables the original randomized R was stratified based on. And we also included the original randomized arm, which was the glycemic control, as a confounder. There's a variable, the reason for children being admitted to the intensive care unit, either due to cardiac surgery, to undergo cardiac surgery, or something else. And clinicians suggested that we focus on this subgroup of patients with cardiac surgery, which I was very sad to do that because it halved the sample size and then ended up with just 700 patients. But the reasons were good enough. Here we ended up with a much more homogeneous sample than using the whole population. The intervention we are focusing on is feeding. So denoting it with A. We have a recorded feeding for every day. That's the T index. And the way this feeding variable is coded, if they receive at least 20% of the target, which we calculate for them based on current guidelines and their body weight and gender and age, we compare it to the actual, and if they are above this target, then we call that feeding. This resulted from discussions with the clinicians. There are those things which change over time. There are those things which are these time-varying confounders, whether a patient has an infection, renal replacement, how their INPOP score is changing, and very importantly, whether they are on or off mechanical ventilation. I haven't talked about the outcome yet. For this analysis, we are focusing on how quickly the patients are discharged. So YT, if a patient is discharged alive by day T. A bit of a complication that because this is an intensive care unit, sadly, they can also die. So MT denotes whether a patient is dead by time T. The first challenge here is that this sounds all very clear and easy, but we actually had to think quite a lot on how these things happen after each other, how discharge, death, the treatment, and the time varying confounders actually happen. And this already requires some thinking of the ordering and some thinking of how the causal mechanism happens here. And the way we ended up representing it is what I'm going to show you right now. So these brackets, the squares showing days. So the first one is the baseline, the first day, second day, and this goes all the way to day 7. And what we assume is that on the first day, everyone is alive and not discharged. So Y0 actually equals 0 for everyone, and D0 also equals 0 for everyone. So neither dead or discharged. And then we measure the baseline confounders, and then we measure the first treatment, so the first amount of calories administered on the first day. So that was the first day. The second day, now we measure whether are they still at the ICU. If Y1 equals 1, that means that luckily they are better and they are discharged. But if D1 equals 1, that means that they died. And then, in case these ones are both 0, then we are going to again observe a bunch of characteristics which changed compared to before. And then we notice, then we observe feeding again. And this goes up to the last week. And this is mostly for notational convenience that we observe one more outcome after the last day. So this is kind of a final outcome. Another way of summarizing this ordering here is using formal notation here. This already actually involves in strong assumptions, and I had to think quite a lot, and I still think I need to do some sensitivity analysis around whether this is actually true. Whether for example, the status of mechanical ventilation, whether when the doctor decides to take a patient off mechanical ventilation, that really happens before the doctor decides how much to feed a child. But for now, we make this assumption. Now, I haven't talked yet about what kind of treatment regimes and treatment interventions we actually want to compare. So I just said that there is feeding and not feeding every day. When trying to do causal inference or any kind of intervention, a very nice way of thinking about causal effects is by coming up with a hypothetical trial. Something, if we had infinite resources and no ethics committees to stop us, we could just run. And we could treat patients different ways, and we could just compare outcomes between patient groups. And that would be our causal effect. In terms of longitudinal treatment, this means that we have to a priori specify a sequence of treatment. For example, a future guideline can be something like that, which says that always feed a child at least 20% a day. That would be in the guidelines. So this could be an a priori specified longitudinal treatment. And then we could run a hypothetical trial and randomize children for this. Formally, again, I'm sneaking in a little bit of model notation. This means that I'm fixing the values of my treatment variable to certain values, small a, and the treatment regime of interest is now defined as a vector, the a bar notation, as a vector of these treatment values from the first day up to the end of follow-up. So the question is, if this is a binary variable a, and we have lots of, we have several time periods, then there will be several, like 2 on the power of 7, if this is for 7 days, different treatment regimes. Do all this make sense or not? So let's see what is a good way of thinking of how to formulate treatment regimes. Oh, sorry, that was a nice graph which I didn't show you. What I'm trying to do with the intervention is actually fix the values of of the treatment node in every single time, and don't let it take on any stochastic values. So an ideal intervention, a hypothetical trial, would just replace the big A's system to small a's. So for example, an always feed intervention would just replace all those to ones. Okay, but how can we more generally think of interventions? Static regimes decide at the study entry a priori what treatment to provide for the whole period of time, regardless of what happens to the patient. So, for example, the previously defined always feed would be a static regime where the elements of this vector would be all ones. Never feed would be all zeros. Feed from day 3 it would be like 0, 0, 1, 1, 1, 1, 1. So these are static regimes. One might think that this sounds a little bit rigid, like putting something like this in a guideline that definitely feed from day 3, but only from day 3. So don't feed on the first 2 days. Sounds a little bit restrictive. So we actually modify this, and we also consider a bunch of regimes where the intervention is required to start with a delay. So as you can see here now, in the first 2 elements of the vector are big A's. So we leave those to take whatever values they would take, which is by nature, and then start intervening from the 3rd day. To start feeding by the 3rd day for sure, and keep feeding. These are all static regimes though, because this decision has been made at the study entry and cannot be changed. Dynamic regimes offer a more realistic and a more flexible alternative. Dynamic regimes are also called individualized treatment rules, adaptive treatment regimes, multi-stage treatment regimes, and they do realize that different patients might benefit from different things, and that actually might change over time. So these treatment decisions should be adjusted continuously. Evolving clinical course. Okay, and this evolving clinical course means that it should adjust based on what actually the patient receives, previous treatment, and how the characteristics change. A very simple one, which we define here, is feed only when a patient is off mechanical ventilation. So as opposed to having constants as an element of that treatment regime vector, now we have a rule. So each element, so here instead of constants, we have a rule, DC, which is a mapping from this patient characteristic to an action. Another example, jumping back to the cancer example, would be start chemotherapy A, but switch to another chemotherapy after progression. So that would be again something that this is a dynamic rule which takes into account the changing patient characteristics. In this example, we are only going to use this dynamic rule. Okay. So now, yep.
So basically, the simple rule says that if BT is 0, then A
is 0.
1?
Yes. Off mechanical ventilation. Yeah, I mean the way I code it is the way I code it is that off mechanical ventilation means that VT is 0 and then AT is 1.
So it doesn't matter what happened in the previous.
Yeah. So this, for example, it wouldn't matter, but it could be something more complicated. That actually the clinician here was originally suggesting something super complicated, like don't feed on the day when the patient is taken off mechanical ventilation, because then it's somehow complicated with the feeding tube, but feed after. This sounded great, and I tried to implement it in the data. Turns out after the patient is taken off mechanical ventilation, they are discharged. So there was no way I could actually observe this treatment rule in the data. So I simplified it for kind of my learning purposes, but this is not the most realistic one. Yeah, so this could go really complicated. Yep. Okay, so we formulated our treatment interventions. We have this hypothetical clinical trial in our head. So what we actually do with it is to generate counterfactuals. So counterfactuals are potential outcomes, are the outcomes in a population where where people would receive the intervention of interest. And we would be interested, so the idea would be to actually be able to measure somehow the average outcome among patients who all receive the intervention of interest. These counterfactuals can be thought of as figs, which is done a lot in some of the statistics literature. So, for example, thinking of a much simpler example, if there is just a one treatment, one time period situation, my potential outcome under the treated and under the control state is somehow already out there. It's somewhere written on a whiteboard. We just don't know about it. And the outcome which will be actually revealed, that will depend on what treatment I actually received. So this is one way of thinking of counterfactuals. Another way of thinking of counterfactuals is by generating them from a structural equation model where we intervene on the system. And by intervening on the system, instead of the observed outcome, I actually observe the potential outcome. So a very simple representation of this is, again, going back to the original example. We are intervening on all these A nodes, and then all those outcomes and all those confounders which are after this intervention node will change their potential values. So they are not these observed blue things any longer, but they are these red things with a small a bar in the subscript, which means superscript, which means that they are now taken up their potential value. And we could actually be interested in treating any of those things as an outcome. We even considered actually. So the first idea was to focus on this confounder, what we call a confounder now, being off mechanical ventilation, and count it up and focus on that as an outcome. For some reason, that's not what we did. We might still do it. What we focus on instead is looking at the discharge status. But both could be done. So anything which is not an intervention node and can take on these potential outcomes can actually be treated as an outcome, and we can look at the causal effect of the treatment on that. So we stick with discharge. So we stick with the potential discharge status on first day, second day, end of day 7. Okay, so now we have our interventions or counterfactuals. We haven't talked about the parameter yet. So what is that we actually want to estimate? So sticking with the discharge status as an outcome of interest, a very obvious and very useful parameter of interest is the so-called intervention-specific mean, which is the expectation of this potential outcome if we intervened on all the values of the A, so all the treatment values. So that would be that's our outcome of interest, the intervention-specific mean, which in this case, with a binary outcome, which is discharge, translates into cumulative risk of discharge by a certain time. And to make life a bit more complex, we are actually interested in this over a series of time points, which will kind of give us a survival curve kind of parameter. So it's not just one parameter. We are interested in cumulative discharge by the end of the first day, second day, third day, and so on. But this is not the only parameter we can be after. We can be also after the risk difference, the relative risk, the odds ratio, the hazard ratio. So for example, the risk difference would be an expectation of the potential outcome under one treatment regime minus the expectation of the potential outcome minus other treatment regime. Yep.
So you have the option also of remaining intubated or remaining in ventilation on day 7.
Ventilation is treated as a confounder right now.
Sure, but you could be within the ICU in critical care for more than the observed period. So you have a form of censoring.
Yeah.
And good censoring be taken into account in this way, in this approach? Because this wouldn't sum up to...
The question is whether we have to do that or not. So what happens if someone is still at the ICU at day 7? sorry, day 8. So we intervene for 7 days, and then at the morning of day 8, we are still at the ICU. That just means that the outcome was 0. So I don't think
there's no discharge, but it doesn't also mean that there was no death.
Yeah. Yes. Yeah. So the death is something we adjust for, but that's not our primary outcome of interest. So but this might help. If someone is discharged, we assume that they can't die. That's actually a small assumption. We talked to the clinician, and there are only a couple of cases where this matters. If they are dead, they obviously can't be discharged, but that's kind of obvious. So this is how we are dealing with these 2 events. If this helps.
I think the other problem is that essentially you're going to estimate the probability, the risk of discharging, but assuming that they're not dead, right? So
Probability.
if somebody dies, then does not participate in the estimation.
Yes. So yeah, actually, we talked a lot about this, how to define its parameters. So let me reassure you here. Again, if someone is dead, they can't be discharged. So from the point on when they die, their discharge status will just remain 0.
I don't know if that's because it doesn't, not really, it cannot not be discharged.
Can we return to this point later of how we exactly deal with this? Because yeah, there certainly has been lots of discussions, and I convinced myself at several points that this is okay. So the outcome is being discharged alive. I don't know whether that helps. So if it's like discharged alive, there's a composite outcome. Kind of.
The death is essential.
That is kind of, yeah, that can be thought of as a censoring. And again, when we started this, I wanted to deal with that as a censoring. The problem was that in this kind of, with this method, the way we think of censoring is another intervention mode. So we would want to fix our observational data by making sure that everyone gets the treatment of interest and they are not censored. And with that wouldn't make sense. So that would make sense for like censoring due to loss to follow-up, because then in an ideal trial we could make sure that no one goes away, but we can't make sure that they don't die. So it sounds much more like a competing risk, I think. Thank you. Yeah, it's certainly a complication, and but let's see. Okay. Where are we? Okay, so we intervene, we have the potential outcomes, and we have a parameter. There's one more target causal parameter, which I just spent 1 minute talking about this, which is the parameters of a marginal structural model. Marginal structural models are often confused to be an estimation method, although it's not an estimation method, it's actually a certain way of thinking of the parameters. And that way of thinking of the parameters is by thinking of how the potential outcome is actually a function of the treatment value. So for example, this is a kind of a dose response function with some link function. If we estimated the parameters of this thing here, then we would come up with the dose response function between feeding and discharge. Nothing guarantees this is correctly specified. Nothing guarantees that this actually makes sense. It's a way of summarizing this relationship. So this can be also estimated. I'm not doing that here. Okay, so I'm focusing on the intervention-specific mean, and for that, really important thing to discuss is how to go from the observed data to the potential outcomes, how to make this jump. And that is identifying assumption which is needed to make this jump. So how we obtain these counterfactual quantities from the observed data. 2 very important assumptions. First one is the sequential randomization assumption, which is actually a generalization of the no unobserved confounding assumption. or the conditional exchangeability assumption, known from a simpler causal inference settings. So it basically requires that the potential outcome is independent from the received treatment if we condition on the history. So among patients who are sufficiently similar to each other in terms of their observed characteristics, we can think of the treatment as good as randomized at every time period. It's a strong assumption. The only way to assess this is to go back and forth with the clinician and make sure that we measured everything, that there are no main other factors which make this independence not true. Positivity assumption is a little bit easier to assess, but still not completely. It basically requires that conditional on a patient having followed the treatment regime of interest up to the previous time point, there is some positive probability to continue to follow it, again, for any combination of history. This can be assessed by looking at it later a little bit. Sequential randomization assumption, this is something where we need to use our background knowledge about the system. Okay, so once we have these assumptions, I need to go back. Sorry. Yeah, so we can estimate. How much time I have? That's not much. Okay, so yeah, so I won't be able to talk much about the estimation. Yes, with the discussion, without the discussion.
No, you have 10 minutes until 2 o'clock.
Okay.
11 minutes.
All right. There are two major ways of attacking this problem from the estimation point of view. One is trying to estimate the treatment-confounder relationship, which is essentially trying to estimate the propensity score, trying to estimate the conditional probability of receiving a treatment in each time period. Another way of doing it is based on the more traditional, no, not traditional, is pretty much doing a regression approach, but in a way which is appropriate for time-dependent confounding. And this is called G computation. Adding the two together gives us a doubly robust estimator, which has a very nice property of being consistent if at least one of the two is right. Okay, so what do I keep here? I think something is... Okay. Inverse probability weighting is what is using the estimation of the treatment mechanism. So I'm not going to talk about this. We are basically reweighting those patients who follow the regime of interest to create a pseudo population to mimic a population where everyone actually followed it. This estimator is intuitive, it's easy to implement, and it can have pretty bad finite sample properties because dividing with the inverse of a probability, if that probability is small, that can give us really large values, and then that can give us really unstable estimates. Another way of approaching it is by combining this inverse probability weighting estimator with also information from the outcome mechanism. And that's what targeted maximum likelihood actually does, which is based on the idea of G computation. And I'm not going to talk about what G computation is, but I'm going to talk about how it's actually done in practice, because it's actually not that hard. So instead of running one regression, when I put everything on the right-hand side, I iteratively adjust for the confounders, one time period at a time, starting from the last one. So the way it's done is we regress the outcome on the full history, take predictions, setting the treatment to the desired treatment levels, save this, take these predictions to the new treatment, again regress it on the history up to one period less. Now we have taken care of one of the confounders. I'm just looking at two time periods here. Again, take predictions, save it, and take average over the baseline confounders. This is only when there are two time periods. If there are more, then there are more steps. Now the problem is how we specify these regressions actually. This can be still misspecified. Don't really know how these things work. And this is where the W robustness kicks in. We can actually update each of these regressions with that inverse probability weighted term I showed you before. And using a certain way, it has been derived to specifically reduce the bias in the target parameter, which is the intervention specific mean. You got all the details there. By doing that, we can expect that if at least this regression or the propensity score was correctly specified, this estimator will be unbiased. These are the steps. All this can be done actually using an R software, which has been developed, and it's actually pretty user-friendly. Last challenge which remains is how to actually still specify these propensity scores and these sequential regressions. So we still, even if it's doubly robust, at least one of them has to be get right, and it has to be correctly specified. And one way of approaching this is by just get the machine to do it and get the data adaptive model selection method, which is optimizing cross-validated loss function. And that's what we do here. Okay, results. So I don't have much time for the results. These are my patient numbers. And the reason I didn't want to waste much more time discussing the deaths is because I don't have that much. I don't know. I know that's not a that's not an explanation, but I think that what we do around the death is probably correct. So what do we have? We have 700 patients starting at the ICU. By day 7, we have only 200 patients left, and that's because they are mostly discharged. So that's a good thing. Feeding. It seems that no one gets fed on the first day, but they increasingly being fed as time goes by. And barely any patients are left who are actually not fed by the end. So it seems that treatment regimes which are interesting and relevant for this data set are those which are gradually increasing feeding somehow. So that's the ones we considered. Okay, so these are some unadjusted estimates of the probability of being discharged alive by the end of day T, so 1 to 7. For two treatment regimes here, one is the never feed regime, and the other one is the feed from day 3 regime, the blue one. Because we feed from day 3 for the first 2 days, these parameters are exactly the same. On the third day, we already see some difference. And the major difference we see is that feeding seems to be harmful in terms of discharge. So those who are fed from the third day, they seem to have a much lower probability of being discharged by the end of a given day. So this is unadjusted for any confounding. So this is what we find with the inverse probability weighting. This disappears, confidence intervals blows up. While at least there is no harmful effect of feeding, which, by the way, was actually the clinician's hypothesis that feeding might be bad. Okay, so this was IPTW. We know that IPTW has this bad finite sample properties, really large confidence intervals. So let's see what targeted maximum likelihood estimation, this putting these two components together, can give us. Well, it becomes more precise, and we again see a little bit of separation between these survival curves at day 3 and 4. So it seems that still there seems to be something going on, that those who are fed on the 3rd and on the 4th day, they are less likely to be discharged by the 3rd and the 4th day. So trying to figure out what's going on here, I considered a wider range of treatment regimes. So you bear with me. This is the regime where patient is always fed from the first day. This is when they are fed from the 2nd day. This is the regime where they are fed by the 2nd day. So the difference between this and this is that here we also intervene on the first day. Here we don't intervene on the first day, only from the 2nd day. Again, from the 3rd day by the 3rd day, from the 4th day by the 4th day. I was hoping to see some kind of relationship between the day of starting the feeding and the discharge probabilities, but honestly, it looks pretty flat. So there doesn't seem to be a significant relationship there. Okay, that was my result. Obviously, there is a potential for unobserved confounding. While we captured some pretty important predictors of discharge, for example, mechanical ventilation, we think that there might be some factors which change over time, maybe some unobserved factors which make a clinician know exactly that the patient will be discharged tomorrow. So maybe don't bother putting down that feeding tube because it would be harder to take it out. This is something this analysis cannot handle. And obviously, it would be nice either for this analysis or for the next one to define further more meaningful dynamic regimes, because so this is actually the treatment of ventilation dynamic regime, which again doesn't seem to be any different from the rest. So just to summarize, going beyond my application, what's really important, kind of a takeaway from this talk, is how to approach evaluations, causal evaluations for longitudinal treatment, or just in general. Think of the causal model. Think of how these variables actually have an effect on the outcome. But what would we want to be an ideal experiment? Link it to the observed data. What do we want? What do we have? Define carefully the target causal parameter. Assess the identification, whether it can be gathered from the data, and then use the best possible methods to estimate. Thank you very much. I don't have time for that. Yeah. Thanks a lot.
Thank you very much for explaining complicated things in a straightforward way. I don't know if we have time for, maybe we have time for one question. Anyone?
Sorry, can you repeat?
Mechanical ventilation use, that's what you mean? So what was the proportion of people that they were on mechanical ventilation, of the kids that were on mechanical ventilation?
Oh, so they all started on mechanical ventilation the first day. This was the inclusion criteria. And then they started being taken off. On the second and the third day, a big proportion of the kids were taken off, like 100 or so, I think. Yeah.
Okay. Thank you very much again.
Thank you very much.